Okay, time to get started with lesson 68, where we're going to be considering probabilities, specifically probabilities of mutually exclusive and inclusive events. Okay, we already know that probability describes the possibility of an event happening. In some cases, the events cannot happen at the same time. For example, when someone tosses a fair coin, there are two possible outcomes, heads or tails. Both outcomes cannot occur at the same time. Two events are mutually exclusive or disjoint events if they cannot both occur in the same trial or experiment. Okay, guys, does that make sense? So let's just remember all the way back to what we first started working with probability, which is that probability is determined by the total outcomes over the total possible outcomes, right? Okay, so that's what we're looking at here, and we're looking specifically today at mutually exclusive, that's where we're going to start, or inclusive events. If we have events that are mutually exclusive, it means that it is impossible for those two events to happen at the same time. The example that we're given is that it is impossible to flip a coin and get both heads and tails at the same time. You're going to get either one or the other. And in that case, where we have mutually exclusive events that cannot happen simultaneously, we can determine probability of those events, okay, by this equation, where the probability of A or B, outcome 1 or 2, heads or tails, is equal to the probability of A plus the probability of B. So really what we're doing today, guys, is we're going to be adding and subtracting probabilities. And we're going to be doing it primarily through the theoretical rolling of a number cube. Now we want to remember that number cubes have 6 numbers on them, 6 sides. I'm sorry this doesn't, your little chart here doesn't have this included, but please, up here we've got the roll of cube 1. Over on this side we should have the roll of cube 2. This one should be cube 1. Okay? So here we have the events of cube 1, the outcomes of rolling cube 1, and the outcomes of rolling cube 2. This is the outcome of rolling a 1 and a 1, a 2 and a 1, a 3 and a 1, a 4 and a 1, and so on and so forth as we look at our chart here. Okay? Okay. With this information here in front of us, and we're going to use this for pretty much all of these examples, we're going to do some calculations. First, we're going to start with mutually exclusive events. And again, here's our formula. Okay, for two events that can't happen at the same time, we're going to add the probability of one to the probability of the other to get the probability of the two events. All right, the two mutually exclusive events. So here we go. What is the probability of rolling either a sum of 5 or a sum of 12 using two different number cubes? So here, these are the sums right here, okay? The probability of rolling a sum of 5 is represented, here are the sums, by these possible rolls. You could either roll a 1 on one cube and a 4 on the other, a 2 on one cube and a 3 on the other, a 3 on one cube and a 2 on the other, or a 4 on one cube and a 1 on the other. So there are a possibility here, there are 4 different possibilities out of how many? And that's what we have to determine here, right? We've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So there are 36 possible outcomes represented in the roll of these two cubes. 4 of them, 1, 2, 3, 4, are what we have here, okay, are the possibilities of rolling a sum of 5 on those two cubes. So that is, as we are calculating out here, the probability of, because here's our or, right? The probability of a sum of 5 or a sum of 12, this is A, this is B, is going to equal, according to our equation, the probability of, I'm just going to say 5, okay, that's the sum of 5, plus the probability of a sum of 12. That's how we're going to calculate it. So the probability of rolling a sum of 5 is 1, 2, 3, 4 out of 36. 4 out of 36. Now if I add that to the probability of rolling a sum of 12, and on my chart here, I've only got one possible roll. We've got to get a 6 on both cubes. So I've got 1 out of 36 tries to get a 12. When I add those together, I get a total probability of 5 out of 36 for rolling either a sum of 5 or a sum of 12. Okay, let's do the same thing here with rolling the sum of either a 2 or a 10 using the number cubes. So in this case here, I'm going to look here. I've still got a possibility, possible. Let me just write the equation out here for you guys, okay? So the probability of the sum of 2 or a sum of 10 is going to be equal to the probability of rolling a sum of 2 plus the probability of rolling a sum of 10. Okay, so we understand what that means. The sum of 2 shows up a whopping 1 time on here, right here. If you roll a 1 on one cube and roll a 1 on the other, that's the only chance you've got. So it's a 1 out of 36 chance for rolling the sum of 2. Now I need to add that together with rolling a sum of 10. So how many times here do we see different combinations we could roll that would give us a total of 10 on those two cubes if we added them together? The answer is 3 out of 36. Okay, so I've got 1 out of 36 chance of getting a sum of 2 and a 3 out of 36 chance of getting a sum of 10. When I add those together, I get 4 out of 36, which I can now reduce to a 1 in 9 chance. Okay, that's the answer to each one of those. Simple enough. That's how we calculate finding the probability of mutually exclusive events. In order to find the probability of what we call inclusive events, we need to add one more step. Okay, so in some instances, it is possible for 2 events to occur at the same time. 2 events are inclusive events or joint events if they can both occur at the same time. If A and B are inclusive events, then the probability of A or B happening is going to equal, here's how we're going to look at it in terms of our formula, the probability of A plus the probability of B, so far same, minus the probability of both A and B happening. Okay, so we need to add that one step. We get these 2 probabilities added together, and we've got to subtract out the events or the times when those 2 events might occur at exactly the same time. Let's go ahead and work it out and see if it doesn't make more sense. What is the probability of rolling at least one even number or a sum of 10 using 2 number cubes? Okay, so if I'm looking at this, what is, now because it's possible that we might roll an even number and a 10, we have to subtract that out of the total. So it's going to look like this. The probability of rolling at least one even number, at least one even, it could be more than one even, okay, or a sum of 10 is going to equal the probability of even plus the probability of rolling a sum of 10 minus the probability of an even number that is also a sum of 10. Okay, that's what we've got to figure out now. So it sounds a little complicated, but it's actually not too hard. Let's look back up here at our chart, and we need to figure out what's the probability of rolling an even number. How many of these are even? Let's take a second. I know it's going to take a second here. I should have brought more colors in here with me. I think I'll just go ahead and use my pencil and I'll shade them in, okay? So if I've got even numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. At least one even number. Oh goodness. If I have at least one even number, you know what, guys? I just did all of that shading for nothing. I hope you didn't do all of that shading in, oh goodness sake, because I read that wrong, sorry. I just shaded in for you all of the even sums. All of the even sums, but that's not what they were asking. So I better be really careful there. Because they were asking, what's the probability of rolling an even number on a cube? So I could roll an even number all of these times, right? In all of these cases, I rolled a 2. In all of these cases, I rolled a 4. In all of these cases, I rolled a 6. In all of these cases, I rolled a 2. In all of these cases, I rolled a 4. And in all of these cases, I rolled a 6. How many of those altogether do we have? Okay, so that's the question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, now that we got that straight, that's the probability of rolling an even number, not a sum, but an even number is 27 out of 36 possible rolls that I might get an even number. Okay, now let's go back and look at the probability of rolling a sum of 10. We've already seen that. Here are the sums. I did do that right. And there are 3 possibilities out of 36 that I could roll a 10. Now they want to know what's the probability of rolling at least one even number or a sum of 10 using 2 number cubes, but not both. But not both. And so I need to subtract out however many possibilities I have of rolling one of these 10s that is also an even number. This is an even number roll, right? This one right here. This one is an even number roll. This one is not. These are 5, so I could roll 2 5s. Neither one of those is even. So I've got 2 out of 37 possibilities. 36. This should also be a 36, for heaven's sake. What am I doing? This thing I was getting ahead of myself there. Okay, so I had 27 out of 36 chances to roll an even number on a cube, plus 3 out of 36 chances to roll a sum of 10, minus 2 chances that it might be both of those. That's going to give me my total probability. Okay. 27, because these are all the same denominator, I can add the numerators or subtract straight across. 27 plus 3 is 30, minus 2 is 28 out of 36. When I reduce that, I could reduce this by a scale of 4, right? This becomes 7 out of 9, and that is my answer. Okay, hopefully my mistake there didn't confuse you too much. Let's keep going with a very similar type of example and see if we can't figure this one out. What is the probability of rolling at least one even number? Okay, so it says now we've got the same idea here. At least I know what that was. Or a sum of 3 using 2 number cubes. Okay, I already know that the probability of rolling one even number, I already figured that out. Not a sum, but just that there's an even number on the number cube, is 27 out of 36. I need to go back to my chart and see how what the probability is that I might roll a sum of 3, because I know that I have to add those together. Okay, so the sum of 3 up here, I've got one of them right here and one here. So there are 2 possibilities out of 36 that I might roll a sum of 3 using 2 cubes. So I'm going to add that. Now, I need to subtract out from here any possibilities that I might have both an even number and a sum of 3, okay? That I might have both. So check this out. If I roll here, the sum of 3 here, then I've got an even number because I rolled a 2. I've got a 2 and a 1 that I rolled, so that one's out. If I roll a 2 and a 1 the other direction, okay, with these two cubes, and I get that sum of 3. Now, both of these things are sums of 3, and they required an even number cube. So I need to subtract out, what am I doing here, you guys? Goodness, this wasn't a sum of 3. I just saw this guy because we had 2 possibilities out of 36, and both of them required an even number. So I got to take them both out. And I end up with a total of 27 out of 36, which I can reduce by a factor of 9, right? If I divide this whole thing by 9, I get 3 out of 4. Okay. All right, I've been doing a lot of recording today, so you have to forgive me for putting weird numbers in weird places, all right? Hopefully this is all making sense. I don't think it's too difficult. It's just a matter of recognizing when we're dealing with mutually exclusive or inclusive events. So let's see if we can analyze that here in our application problem, okay? So our application problem here says that we've got a town containing 5,000. We've got 2 application problems actually, one here, and they're different. 2 different problems. Okay, so we have a town containing 5,890 people planning to vote for candidate A, 6,910 planning to vote for candidate B, and 10,050 planning to vote for candidate C. In a random gathering of 200 people, how many would you expect to be voting for candidates A or B? Let's think through this for a second. The first question we need to ask ourselves is, are these events mutually exclusive or inclusive? So can someone vote for more than one candidate at a time? Or, this one here, inclusive, or are they mutually exclusive, meaning you can only vote for A or B? Those are the only options. And the answer is they are mutually exclusive. No one could vote for A and B, right? They can either vote for A or B. Both of those things can't happen at the same time. So let's figure out our probabilities here, which is the total outcomes over the total possibilities, right? Okay, so let's figure out how many people are in this town to start with. So we've got 5,890 planning on voting for A, 6,910 planning on voting for B, and even though they're not asking us about candidate C, we know that there are still 10,050 who are voting for C. So that's a total number of people that we have to choose from. Okay, we're going to do a random gathering of 200 people here. So we don't really know if it's going to be A, B, or C. So we've got to know how many total people we're dealing with here. So let's go ahead and add that up. 5,890 plus 6,910 plus 10,050 is going to give us a total of 22,850. Okay? So I added all of those up. Now, we want to know, how many would you expect to be voting for A or B? Okay? For A or B. A, we know, is 5,890 out of this number here. This is the total number of people who are voting. 22,850. Okay? I'm going to add that to the number who are planning on voting for candidate B. This is the probability of people who are voting for candidate B out of 22,850. And when I add that all up together, 5,890 plus 6,910, I get 12,800 people voting for A or B out of a total of 22,850 people. When I do that division, 12,800, and I divide that by 22,850, I get approximately 0.56. When I do when I round to the nearest hundredth, I get 0.56. Okay, so about just slightly over half of the people who are gathered there are going to be voting for A or B. So what I need to do now, because I know that there are 200 people that we're polling, is I'm going to take 200, those 200 people, and I'm going to multiply it by 0.56, because we know that's approximately the percentage of people that's going to be voting for A and B. And when I do that calculation, I can see that about, or approximately, so if you want to use the fancy little approximately sign, because again, we can't have a portion of a person, right? Approximately 112 people will be voting for A or B. All right. Wonderful. So we just needed to make sure that we got this number right, and I think we were going to be in a pretty good position here to be able to calculate out about how many, okay, once we got that percentage, about how many of the 200 would be voting for A or B. Let's change the example now from people to marbles. Haley has a bag of marbles. 13 of them have yellow in them, 16 have green, 23 have red, 8 have blue, and 6 are multicolor. The multicolored marbles have red and blue. If Haley randomly selects a marble, what is the probability that the marble will be red or blue? All right, first thing first, we need to know how many marbles are in this bag. Okay, so she's got 13 yellow, 16 green, 23 red, 8 blue, and 6 multicolored. So let's go ahead and add all of those up. And when I put those in my calculator, I got, oh goodness, I made them, this is where I should have been careful. Here, there is my total possibilities, right? 13 yellow, 16 green, make sure I get this right, 23 have red, 8 have blue, 6 are multicolored, but these 6, now here's where the tricky part was, and this is where I just almost made that mistake. These 6 are included in these because it doesn't say that they have only yellow or only green or only red, that 6 are multicolor, meaning these 6 are included. We don't know exactly how many, right? But they're included in the number here that have these other colors in them. So when I find the total, I'm not going to include those 6 because they're already included somewhere in the count here. All right, so when I add up 13, 16, 23, and 8, I get a total of 60 marbles. So she's got 60 total marbles that she's drawing from. In order to find the probability that the marble will be red or blue, I'm going to add together the probability of drawing a red marble. Remember, there were 23, so there's 23 out of 60. To the probability of drawing a blue marble, there are 8 of those. And I need to subtract out the probability of drawing a multicolored marble that's got red or blue in it. And I knew that there were 6 of those, so I got to subtract that out. Okay, now when I do that math, 23 plus 8 minus 6, I get a total of 25 out of 60. When I reduce that down, I can reduce that by a factor of 5, right? So if I divide both of these numbers by 5, I get 5 out of 12. The probability of Haley randomly selecting a marble and having it be red or blue involved adding the probability of drawing red to the probability of adding blue and subtracting out the probability of drawing a multicolored marble, which includes that red or blue. So altogether, she has a 5 in 12 chance, once I reduce that fraction, of drawing either red or blue. All right, guys, that is the end of our probability lesson for today. Please go ahead with your whiteboards, with a partner or on your own, and complete practice problems A, B, and C. Make sure Mrs. Bryden sees those. And the 16 problems for lesson 68 will be due at our next class period.